Hello, here, hello here, hello to those watching in the future. I'm David, I'm the coordinator of the Maths Learning Centre at the University of Adelaide, and this is a revision seminar for engineering, differential equations for engineers. It's semester 1, 2021. And people want to know about PDEs and various other things relating to. People are going to be entering the seminar as we go, and that's okay. Rules are you can leave at any time, I won't be offended. I know that you might have somewhere to be, and it is always okay to ask me questions. Maybe wait till I get to the end of a sentence, but then feel free to say something. If I have made a mistake, like put a minus in the wrong spot or written an X when I meant a Y or something like that, please tell me immediately and feel free to interrupt me in the middle of a sentence if that happens. Okay? Do not wait 10 minutes and say, David, did you really mean a 2 in that spot? Oh, no. So tell me straight away if there's a maths calculation error or anything else of that, or a notation thing. I will not be offended if you ask me to move my page or to write me to, they're good things too. Also, any question that's related to what I'm currently talking about is okay as well. I will try to stop every 5 to 10 minutes and ask you if you have questions. And sometimes I will tell you to ask a question and not ask you. Okay, but just they're the ground rules. It's your seminar, it belongs to you, so please ask when you have something to ask. If I feel like I don't want to answer it, I'll just say so. Okay, all right. So this course, the way it is run this semester, has a big bit about ordinary differential equations and various different methods for dealing with those, and there's power series and stuff, and Laplace transforms come into that as well. And then a big bit about which is shorter in time but has more stuff in it, that's about PDEs. And PDEs are partial differential equations and they are differential equations that involve partial derivatives. So that's a helpful name. And you know, they tend to have things like something like that, for example. It'll have some function, even reading this I can tell there is some function called capital T, which must be a function of both little t and little x, because I was able to do partial derivatives with respect to t and x. And so when I read this, I can see there's a function of both time and position, and I'm able to do partial derivatives of both of those. And those partial derivatives are related to each other in this way. And apparently, the physics of the situation tells you that this differential equation must be the truth. And it's much easier, because of the way the physics works with accelerations and stuff, my understanding of it is it's much easier to figure out the differential equation and how the derivatives are related than it is to figure out what the function actually is in a situation. And that's why we have differential equations and why we care about solving them. So, yeah, and they tend to happen with vibrations a lot in this course. So there is a list. I went through the notes and tried to find all of the situations that they specifically mentioned, and these are the situations that they mentioned, that the PDEs were used for in the notes for this course. There was a string on page 99. There were drums that started on page 104, both rectangle and circle drums. There was heat, and there was electromagnetism stuff. Right. These are the ones that had specific examples in the course. And each of these situations had terminologies to go with them, which in the assessment during the semester would turn up in the Mobiuses and the written assignments, and they'd say, it's a string, floobity flibbity foo is 5, and singity sobby thingamajig. And so you'd have to figure out what was going on. And that's, yeah, okay. So what I'm going to try to do is collect together from the notes the terminologies that go with these things at some point in this seminar. All right. Cool. And I might even do it now. So stepping back, the idea of this is that there is some function which is a function of both t and x, and usually the t is time and the x is position. And so that t could be temperature, for example, and this would be saying that maybe this is temperature and this is time and this is position. And it's saying that the temperature changes as time moves forward and it's different in different positions. So I'm imagining there is something that only has one variable x to say what position it's in. So it must be a bar or a string or something like that, something that's line shaped. Because it's only got one variable x to say where I am on it. And so if I stick at a particular position and I follow in time, the temperature will change. It might get hotter and hotter, it might get hotter and then get colder, it might get hotter and hotter and level off, I don't know. And at each position, the temperature will change in a slightly different way in each position. But on the other hand, if I stick at a specific time and I track along the x, there will be different temperatures at different places. And so both position and time is going to change what the temperature value is at the moment. All right, cool. And so a lot of the, no pun intended. So a lot of the things they tell you that they're heating it at one end or the other, and the heat will travel inwards, and it will be different temperatures at different times. There's not much in this picture, but I'm hoping that it was helpful. So I really want a formula that tells me exactly what the temperature is at a particular location at a particular time. That's the goal. Okay. And that's true of all of these situations. There may be 3 or 4 variables involved. It's almost always 2 position variables and 1 time variable, and then the outcome variable as well is whatever it is. So, okay. So this is not enough information to figure out the formula with x and t. And this goes all the way back to when we did derivatives and integrals the very first time you learned them. When you integrate something, there's always like a plus c. And so you can't figure out exactly what the function is if all you have is the derivative, because there's lots of functions that have the same derivative. Same deal, there's lots of 2 variable functions that have derivatives, their partial derivatives related in this way. So we need extra information to figure out what's going on there. I would expect to need 4 pieces of information here because there are 4 derivatives in this picture. 2 t derivatives, one after the other, and 2 x derivatives, one after the other. I expect to need 4 extra bits of information to figure out exactly what the function is. So that's my understanding of how this works. Okay, so we need also conditions. Okay, and this is where these situations that they talk about are tricky to interpret in a written piece of text, because the conditions will be described using specialized terminology for each of these situations. And so that's what we want to figure out, how that works. The conditions will either be that, well, the conditions will be of several flavors. They may be that the value of the outcome function at a location. They may be a value of t at a time. And usually it's a value of t at a location, and it's always that value no matter what the time is. For all time or for all locations. What they may do instead of telling you a value of t at a specific location at all times, or a value of t at a specific time at all locations, what they might do instead is give you a function that tells you what t is at every location as a specific time. So this basically, that's the deal. And these two things could either be a number or a function, basically. That's how they tend to look. So things that happen when time is 0 are called initial conditions. Because initial means at the beginning in English. And when the location is 0 or some other value, those are called boundary conditions. And that's because it's saying, well, this is the boundary of my string. It stops here, that's the edges, it's the boundary. But if you're not sure, you can call them all boundary conditions, because, you know, the beginning of time is still the boundary of time, and so that's okay. But if you're really interested, that's usually the rules. You sometimes have information of what happens at the end of time as well, but I don't know what they're called. Final conditions, I guess. But I've never heard that phrase ever, so they're probably still just called boundary conditions. Initial conditions when time is 0, everything else is a boundary. Sorry? Yeah, or you only care about what happens when t gets to 1 hour. And so nothing after that matters. So, yeah. But t approaches infinity would be, you know, a final condition, final destination. Right. Cool. I'm just making up crap at the moment. All right. How are we feeling? Good. I'm going to try and look at these things in the notes. The notes will not show up very clearly. Oh, I have an electronic version of it. Oh, wow. Yikes. You can do it. Okay. Courtesy of one of the students. Thank you very much. Because I don't have access to the MyUni in this course. It makes students feel useful when I ask them for them, though, you see. All right. Okay. A guitar string. So this is one of the classic situations. We're going to try and figure out what the terminology is that goes with each of the pieces. Give me a sec. There was another thing here. Okay. So vibrating string, it should have as its variables x and t, where x, this is where x is 0, this is where x is however long the string is. And the function, damn it, sorry, I'm not sharing things correctly. I'm just going to share my whole screen. And then I can switch between them without actually changing the sharing. So that's a vibrating string. It's a line, it's a string, it changes as time moves forwards. So there will be something which is a function of both the position and the time. Okay, and what this particular example has is it calls this function v, which is confusing because the v is not velocity. The v stands for vibration. Yes, vertical displacement. So if you like, you could call it vertical displacement. And what they mean by displacement is how far away the current location of the string is from, oh crap, thank you. How far the string is from its position when it's flat. Now, vibrating strings vibrate do not vibrate much. We can't see the vibration, but that's important because the model only works if the vibration is small. Yeah, so at a particular time, it might look like, you know, whatever it looks like, and then at another time, it might look like this or whatever, and at different times, the string will be slightly different shapes. And at each moment and in each position, you can figure out how far the string is from its normal straight position. That's the idea of what's going on here. I will say things extremely confidently because that's how you do it when you do a lecture, but I may sometimes change what I say confidently later. So, but just at the moment, that's my understanding of what's going on. And the equation that goes with this is on the screen just here. I'm going to write it on my page as well. Yep. This equation. And this is the one-dimensional wave equation, according to what the notes say. Okay. So this is saying that how much if I'm at a specific spot, the speed at which the string is moving up and down, sorry, the acceleration of the string up and down is a multiple of the rate of change of the velocity of the vibration when I move this way. I don't know why. I'm sorry, physics. So there is some reason why they ought to be related. Good-o. But that's what it is. Okay. Sweet. But this one is about imagining what the string going up and down at a specific spot. This one's imagining at a specific time how quickly this curvature is. Because this is about the graph of the shape at a particular time. And this is about the speed at which it's going up and down at a particular spot, because they're partial derivatives, the other one's constant. Okay. So if your lecturer in say, an assessment of some sort says there's a vibrating string, this is the equation that goes with it. Okay. And the name of this C is the phase speed. Pretty sure? Let me just look. Doesn't say, but it did say back at the very beginning when you talk about the wave equation.
So is C squared for waves like with temperature or like
apparently for a string, it's always the tension divided by the density, where tension is a force. So you could imagine someone saying to you, there is a string. It has a tension of 50 newtons and the density is 5, I don't know, kilograms per meter. Because it's a string, it doesn't have. kilograms per meter. What's the equation? And you go, aha, c squared is 50 divided by 5, so 10. I don't know. I don't know if they're going to ask that, but that's where the terminology goes, apparently. Okay, so here we go. Now we can imagine why the conditions are the way they are. So this equation is not enough to figure out what this string is doing, but we do have some information about a string. If it's, say, a guitar string, or a double bass string in my case, it would be, my double bass's name is Bubbles, by the way. It would be held in place at both ends by the things that hold them in place. And so if I imagine what's going on at this point and how far the string is moving up and down at this point, it's not. And so at this location, there is no, the value of V is 0 because it's not moving. It's a boundary condition. So fixed at both ends means that the V equals 0 at x equals 0 for all time. So V of 0t is 0. And it also means that V of whatever the length is, t, is also 0 because it fixed at the other end too. Right. How are we doing? Is this helpful? Okay, good, just. And so that's, yep.
Do we have to assume that will that be provided in the example if these are the conditions of the string?
I have no idea what will be provided in the exam. Okay. But if they say a vibrating string, then I think you should assume it's fixed at both ends.
I think they call it driving with boundary conditions. And like, yeah, that makes sense. You can't do it with that. For sure. Yeah.
Yeah. So worth pointing out in this practice question, it doesn't say, and you're just going to have to assume. Yes. So I assume it's fixed at both ends. All right. Okay. These are really excellent questions. I'm sorry I can't answer some of them because I just don't know about how they've arranged their exam. You're in the proctor trial, right? Mm. When the recording turns off, I will tell you my feelings about that. Oh, not that you don't know, I've expressed it a lot. Okay, so that's not enough information to solve my differential equation. It's got 4 derivatives in it. I'm going to need 4 conditions. And so I need to know some other stuff. And that other stuff is usually concerned with what shape the string is when you start watching. So you go, I've come into the room and I've plucked my string, and so it is a triangle shape or whatever it is. And so I will now watch what happens after that to see what shape it becomes. And so the initial condition, so the shape of the string at time equals 0, that's the initial condition. And it will be the height of the string based on the value of x at time 0 will be a function, usually. And that's what this bit here means. V x 0 is a function. But what that function is describing is what shape the string is when you start watching the string. Okay. So in this problem, this is saying that V of x0 is this function. And that's what it means by initial displacement. So let me just talk about that. This is the displacement, because that's what the V stands for, how far the string is displaced from its original position. And the time being 0 means it's initial. So if you're looking and it says initial displacement in this context of a string, the outcome variable is displacement, and the initial means that the time is 0. And if they say the initial displacement is a function, velocity, not velocity, the displacement V at the initial time will be that function. Right. I'm so happy actually to do this. This is making so much more sense to me. This semester was, yes. Okay. All right. So it says also that the other one will be V sub t at x0. Will be the other one. What does that even mean? Oh, that's the speed at which the top of the wave is moving. No. No, that's the speed of the string up and down at the particular location x, and it's a different speed at every x. Okay, right. So the speed of the string at each location at t equals 0. So this is the initial velocity, and it's a velocity because it could be pointing downwards or upwards, so it could be positive or negative. And so you've got the vertical displacement differentiated with respect to time, that's velocity. And that's initial. And it's sometimes a function and it's sometimes a number. So this could be function or number. So it could be at the beginning when you start watching, it's not moving at that exact moment. So in this problem here, see how it says 0 initial velocity? That would mean that V sub t of x0 is the number 0. Right, that's what that means there. So if I was reading this, I now have everything I need to know about this situation. I might write it on my paper because I don't want to type on that. Let me just go back to the paper. Where is it there? But I just need to say this again for my own self. So here we are at time equals 0 at this spot, and the velocity will be telling me how quickly the wave is, the vibration is moving inwards or outwards at that moment. That's what you're saying? Okay, cool. And it might be different at different places, which is why it's a function. Or it might all be 0 at this moment, which is why it might be 0. That at every point on the string, when the moment I begin watching, it's not moving at that moment, and so therefore everything is 0. Okay, cool. So let me just do this example here. I'm just going to write on my paper in a second. So string length 1, phase speed 1, 0 initial velocity and initial displacement x1 minus x squared. Okay. Okay, so the length is 1. Okay, and the phase speed is 1, so that means the c is 1, and so the differential equation is this. I'm going to assume it's fixed at both ends because they didn't tell me and I just you know, I'm going to just assume it is. So the displacement at the position 0, no matter what the time is, will always be 0. And the displacement at the position 1, no matter what the time is, will always be 0. Should it? No, they're both straight V in the example.
Just the one above it though. Like, so the equation above it for the wave. So on the left hand side is t and the right hand side is x.
Yep. Oh yeah. That should be an x. Is that what you're saying? Yeah, gotcha. That there is an x.
Yeah.
Right.
Thank you. You did what I asked. Thank you. Okay. And I've been told the initial velocity is 0, and so the displacement differentiated with time, that's what velocity is. At time 0, and no matter what the position is 0. Because I didn't mention the position, so it must be 0 everywhere. And the initial displacement, so that's saying that the displacement at time 0 at the position x comes out to this. So this is telling me that I arrange for this string to be this shape when time is 0. And I hold it still in that shape, and then I let it go and see what happens. That's the story that this is telling. Now, it is theoretically possible to use the process of separation of variables to solve this differential equation. I shall not do that. I have lots of videos on separation of variables. And in fact, I don't think your lecturer wants you to do that either, because your lecturer did it for you. Watch. Blah, 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 blah. Here we go. This. So your lecturer figured out along the way, I'm just going to write it down, that omega n is c pi on L, and lambda n, no, omega n is just n pi on L, and lambda n is c n pi on L, and that's what I've got at the top here. And the solution is this. V of xt is some constant times cos of lambda nt plus some other constant times sine of lambda nt times sine of omega nx. That's this bit here.
Is that for all waveforms, all strings?
That is for all vibrating strings fixed at both ends. Yep.
I know in some cases, like the last written, actually wants us to work through some of those steps. Is it okay that they haven't asked us specifically just to jump?
Yep.
Last thing, yeah. Okay.
If they haven't asked you, then I think they expect you not to do it yourself.
You can,
But if they said use separation of variables, then you would do the working. Because just writing this down isn't using separation of variables, it's using someone else's separation of variables. So that's my instinct as to what they're going to do. Yeah. All right. So here we go. A new terminology has appeared. This number lambda n is called the normal frequency. There you go. I'm going to try and make sense of that. Well, cos of t would happen. Cos of t would happen once every 2 pi. Like it would make it would run through all of its values every 2 pi. twice every value actually technically, but it would run through the same pattern of values every 2 pi. And so cos of lambda nt would do that lambda n times faster. And so that's what they're talking about, why it's a frequency. Yeah. Normal, I don't know, you've got to pick a word. So normal will do. Yeah. Apparently the set of all the frequencies is known as the spectrum. Oh crap, this is not this is just Vn. This is just Vn. The actual V is the sum of all of those infinitely many things. Right. Yeah.
That's what the solution says. They actually go through the summation of.
Yeah.
So the sum of all the obviously
So V, the actual V is the sum from n equals probably 1 to infinity of this. Yay. I would guess that the Bn and the Cn would come about from knowing the 2 initial conditions. So if you look at the working that produced this, the omega n appeared when you solved the function involving x. And so this lambda n was caused by this omega n, and therefore the lambda n was caused by the fact that it's fixed at both ends. And this is caused by the, well, we don't know what's going on, but whatever these numbers are is caused by the initial conditions. Or possibly the other way around. No, that's right. Okay. Yeah. Right. So if we had this situation here, you could conceivably skip to this point. So if I had this situation here that I made, we've got this differential equation with these conditions, I could skip to this point and know that Vn of xt is this thing, Bn cos of lambda nt plus Cn sine of lambda nt times sine of omega nx, where the omega n is n pi on the length, which was 1, and the lambda n was c n pi on the length. And so I could sub them in if I wanted. But I also know that v of x0, vtx0 is 0. So I know that the real solution is the sum of all of these things, but I also know that if I do a derivative of something, then I do the derivative of all the pieces separately that got added together. So I'm allowed to apply that derivative to each of these bits separately. And because this is equal to a number, I'm allowed to use it before I do the sum sign. That's the general rule. As opposed to equal to a function, which I'm only going to be able to use after I've done the sum. So, oh crap, kill me now. So this counts as a constant because it doesn't have a t in it, so it'll still be there afterwards. The cos became a minus sign, but I also had to multiply by the lambda n. The sine became a cos, but I also had to multiply by the lambda n. And then I know that Vn sub t x0 is, that bit goes away, and I get cos times 0 is 1, right? And this is supposed to be 0 no matter what x is, which means that the Cn has to be 0. Yeah. Yay. And so actually my Vn is really that. And therefore my V is really the sum of all of those things. Like that. Sorry? Yes, I can. And I will. Give me a moment. It'll be bad. Ready? Here we go. Okay. So this was based on this story here. So the initial displacement is this now. When I put in t equals 0, I get that. And I get this. And this is supposed to be equal to x times 1 minus x squared. Watch very closely. This function has been written as a combination of a whole lot of sines. It's a Fourier series. Thank you. This is a Fourier sine series. It's not just a, it's the Fourier sine series for this function. And so B1 will be the first Fourier sine series coefficient that belongs to this, and B2 will be the second Fourier sine series coefficient that belongs to this, and so on. And since this function is not currently written in terms of sine, there will be infinitely many B's. And so Bn is the coefficient of sine of omega nx in a Fourier series for x 1 minus x squared. That's what it is. And so therefore it will be the integral from 0 to L, which is 1, of 2 over L of the function times sine of omega n x dx. Whatever that integral is the answer for Bn. I choose not to find that integral.
Wise decision.
Right. Right. So I will say, yeah. So if someone in the exam, they're probably likely to say, what is an expression for Bn? This is the expression. That's the whole expression, just stop. Okay, so what did we get out of this? Our terminologies were that there was this thing called the phase speed, and that's the C in this formula. There was tension and density, which go together to make the phase speed because physics. There's the fixed at both ends, which caused these boundary conditions because it's at the boundary of the string. And there was the initial displacement, which is the shape of the string, like how far it is from the center to begin with at 0, and the initial velocity is the derivative of displacement. And there is a shortcut based on someone already having done part of the separation of variables. If you're very fast at separation of variables, which would be your superpower, then you could do that. Yep.
You can skip to the conditions because it's a perfect run. So you don't have to prove that
Oh yeah. So you're saying that when you do this bit with the separated into this thing, and you're saying that because it's fixed at both ends, that automatically causes this.
Yeah.
And you don't have to worry about the k being positive or 0.
Yeah.
Okay, cool. So that was when he did the Sturm-Liouville thing, and the shortcut for the Sturm-Liouville is that if you have a second order DE exactly like this, f double dash minus k times f equals 0, and you have information about some linear combination of f and or f dashed equals 0, then you are guaranteed to get a cos something plus, yeah. Anyway, if it's equal to 0, the original function is equal to 0 at both ends, it'll automatically come out to be a cos plus a sine. Right, okay. So that was one situation. How am I doing? Oh my goodness. All right. Drums. Drums started on page 104. Drums. So, firstly, they call it a drum lid, which is the top of the drum. Drum lid. Okay. I have heard in some places in the world, in some courses, this being called a drum membrane, but if your lecturer's not paying attention, maybe they'll cut and paste that from somewhere that they stole their exam question from online or something. They don't do that. Okay. So this is the same as a string in the sense that the equation is similar. It has a dv on dt, dt squared v on dt squared, and it has a d squared v on a dx squared, but it's also got a dy squared because now we have some sort of shape which is either in your course a rectangle or a circle, and there are x and y coordinates. And at every x and y, the drum lid is vibrating up or down from that position. So that's the third variable. The outcome variable is the displacement vertically, still vertical displacement. So we have now that the vertical displacement we're assuming it's vertical, but it doesn't matter that the drum is sideways. It's just that it's vertical relative to the drum. And it's a function of both the position and the time. But you need two numbers to say where the position is. So just so it's a little easier to see what I'm talking about, this is my thing that isn't a drum. And there's my drum membrane. And here, when the drum vibrates, it goes up and down. That's what it means by the vertical displacement. Here in the center, it might be vibrating up and down the fastest. Here at the edge, it might be vibrating up and down less. Yep.
Really, really silly question. But like so like analogous to a top-down drawing, that's in like the z-axis.
The z-axis is pointing at us.
Yeah.
Yep.
So that's the point.
Yeah. So that's the difference between my string. My string would, I'm really looking at it this way. That's going up and down here. Yep. Sweet. Okay. Right. So back when I did my string, the up and down is here, but since it's only got one variable, I can draw it here if I want. Okay. Right. So what does it say about my drum? It says that the differential equation is this, regardless of the shape. It says that it's, I'm copying it off the screen there. It's written there on the first line that has mega maths in it. Okay. The omega they're talking about is the region that the string is, that the drum takes up. So when they say this thing is omega, capital omega, or this thing is capital omega. I don't know why omega. It's the end of the drum. Because omega is like the last letter in the alphabet, like the alpha and the omega. It's the, anyway. It probably doesn't make any difference. Okay. So, in the same as the string, we're going to assume that the drum is held in place at its edges, which means that the position of the displacement at all of these places is going to be 0. And the displacement at all of these places is going to be 0, or whatever shape the drum is. So when it says here, v equals 0 for xy in the boundary of omega, that's what that symbol there means, that delta. That delta there stands for, in this context, the boundary of. You probably never need to use that notation again in this course. And it won't probably turn up in your exam, but that's what it means, just so you know. And then we're going to impose that the displacement, vertical displacement, is some function of x and y. That's the shape of the drum at the beginning of time when you start watching it, same as for the string. And the velocity of the drum at the initial time is going to be a certain thing. And I would almost guarantee that any question that you are given will be 0. Can't be sure, but I reckon it will be. Because almost all situations when you have a drum, you know what, it's not moving when you first hit it. The moment you push it, you hit it with your mallet, and at the moment you let go, it's not moving at that spot. Yeah. Well, it's v, the sub t is the velocity, is the derivative of that with respect to t. So remember back in Maths 1B when you did, no, it doesn't matter, but if you do, Vt is short for this. Just a second. V sub t is short for dv on dt. That's a notation that people use. So in a technical sense, the actual original equation is Vtt is c squared Vxx plus Vyy. That's the short version of that.
What's that in relation to the time?
So this is saying So this v is a distance, and the derivative of distance with respect to time, this is distance over time, which makes it a speed. Yeah. Or a velocity if we're using fancy words, because in physics a speed doesn't take into account what direction it's pointing. So it has to be a velocity because it can be minus. All right, so that's just some thoughts about notation. And so we're going to use the same same conditions is that v of x, y equals 0 if x and y are in the boundary. And it may be quite difficult to describe what it means to be in the boundary. But that's a boundary condition, and it's literally at the boundary. And this may cause there to be several separate conditions depending on the shape of your boundary. I'm going to do that with the rectangle lid in a minute. And v of x 0 is 0. Well, x and y and oh crap of all crap. X and y v of x and y and time is 0 for x and y in the boundary and for all time. Because no matter what the time is, if you're on the boundary, then you're not moving. So on a rectangle, if you've got a rectangle that looks like this, 0 up to A, I'm going to actually give it a name, 0 up to 4 and 0 up to 5, then whenever your x coordinate is 0, that's the edge of the drum. And so we'll have v edge of the drum time is 0. It doesn't matter what the y coordinate is, it'll always be fixed along that spot. It'll never be moving there because I'm holding it in place at that spot. And then v of, so that was a crap of, x is 0. And over here when x is 4, that's 0. And down here when y is 0, that's 0. And up here when y is 5, that's 0. Right, I got it right eventually. The locations are when x is 0, and when x is 4, and when y is 0, and when y is 5. I reckon writing that on the diagram would have been really helpful to me. Yes, because then I can sub in x equals 0 and make it 0. Sub in x equals 4 and make it 0. Sub in y equals 5 and make it 0. Sub in y equals 0 and make it 0. Sweet. Okay. And then normally you would expect that the velocity at time 0 would be 0. So this is 0 initial velocity, and this would normally be a function of some sort. But it would have to be a function of both x and y. And that would be the shape, the initial shape of the drum. They won't call it shape, they'll call it the initial displacement. Or the initial displacement, which is based on my handwriting. Okay. So omega is a set of x, y's where x is between 0 and a and y is between 0 and b. My drawing, the a is 4 and the b is 5. There are boundary conditions. I wrote them all out separately as 4 separate equations. That makes more sense to me than this. And that's nice because 4 separate equations will cover 4 of the derivatives. And I've got 6 in my original equation. So this original equation here has 6 derivatives, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 conditions. Okay, cool. Figured it out? Okay. Oh, wow. Wow. So we separate it into f, x, y, and g. And then we separate that one too. That's the craziest stuff. I have a feeling they're never going to get you to do that by hand. They're just, so remember, part of the purpose of this course is to just tell you where things came from. They believe that doing the mathematical calculations for some of them will make you understand the things better. And I think sometimes people put maths in engineering degrees because they, when they were learning to be engineers, had maths in their engineering degree and everyone should suffer. Not that maths is, you know, something that causes one to suffer. It's being examined on maths that causes one to suffer. Yes. That, yeah. My instinct is you're more likely to get a string question than a two-dimensional drum question, but if they mention a two-dimensional drum question, you're going to just have some things from the notes to say this is the answer. Because that's what happened in the Mobiuses. Mobii. So when it says natural frequencies here, that is the, I don't. It's analogous to the string. The string vibrates at certain frequencies, and so does the drum. But the drum's frequency is Pythagoras on the two x and y frequencies. Right. And we have a new word. We have a new word we haven't seen before called the normal mode, which is apparently the solutions. It says that Vmn of x, y, and t is this. So my instinct is that that's what V is for a particular m and a particular n. In the same way that with the drum, with the string, we had V for a single n, and now because there's two directions, there's an m and an n. And when we add all doubly infinitely many of those things together, we'll have a sum from m equals 1 to infinity and a sum from n equals 1 to infinity, two sum signs. That will be the solution. But as far as I can tell, they haven't actually gotten to the point. Oh, look, they just combined into one sum to make it look less scary, but that's really two sums next to each other. Sorry? What? Yeah, they're just, I don't see this often enough to know if it's standard. It probably doesn't appear very often at all, and so people just make up what they want. I find it confusing because I can't tell if the m and the n are changing at the same time or if they're changing independently of each other.
So you don't know if they're changing, so one could be 1, the other could be 2.
I think that's what's going on. Yep. Yeah. So all of this is just making you believe that the maths is real. And so it produces this, which is not really more edifying. But it seems to me that the key important information from this that we get is this lambda mn equals thing, that they are the frequencies. And if the initial shape of your drum is the right shape, then only some of those frequencies will produce functions that actually exist. So you know, if your function's already a sine of something times sine of something else, then only one of these is actually going to come out to be not 0. So I have a feeling that if the drum is exactly the right shape, then most of the BMNs and most of the CMNs will be 0. And only some of the frequencies will actually turn up. Yes?
Is that the natural frequency only for a rectangular drum, or is that also for a circle?
That is for a rectangular drum.
Okay. So,
I know this because it's got the A and the B.
okay.
And the A is how wide the drum is in the X direction, and the B is how wide the drum is in the Y direction. If it was a circle, they'd be the same. Yep.
Are we using polar coordinates for circular drums?
That seems likely. That these are Cartesian coordinates, an X and a Y for each position. Here's the circle. Look. Instead of using X and Y to specify the location on the circle, I use a radius and an angle. And now, at this radius here, the drum is held in place. And so when the radius is whatever the radius is, they've called that capital R for the big radius. The displacement is 0, no matter which angle you're at. That's what that is. I'm going to draw it on my piece of paper as well.
So that big R is when the value of R is greater than little r.
I'm going to talk about that. Here is my circular drum. It has a radius of, let's say, 7. The little r is the radius of the point on the drum that I'm thinking about. So if I have a random point on the drum, say here, that little r is this far away, which is 2. And this point is at distance 1. So this is little r equals 2, little r equals 1. This point here has little r equals 7. The big R they're talking about is the maximum possible radius when you're on the drum. Because it's a big R. That fits the, anyway. That's really what it is. The little r says whichever r you're thinking of, the big R is the biggest R. Okay. And so what they're saying is that the vertical displacement out of the page, when the radius is 7 and when the angle is whatever you want, and no matter what the time is 0. And it's a boundary condition because this r equals 7 describes the boundary of the drum. So I've written it as little r equals 7, but it's traditional to actually just do that. But that is r equals 7, which is the boundary of the drum. All right. They've chosen the theta to be between minus pi and plus pi. You could have chosen it to be between 0 and 2 pi, and that would have been fine. You just need to choose a range of angles that covers everything. But I don't think we're going to have to solve this ourselves. They've had to actually do a change of variables to produce this brand new version of the equation, and they've look at all this fun. All right. Are you ready? Yeah. They've managed to so when they separated it, it produced, you know, a thing, a function of the radius and a function of the time, and the theta didn't come into it because you're assuming the drum behaves the same in every direction, and so the theta tends to disappear. Because it's symmetrical in every direction, you just go, it doesn't matter what direction I'm pointing in. But the maths bears it out, apparently, because anyway. So you start with this. Yeah, don't get me started. And so what I produce is this differential equation with the f's, f double dashed 1 over r f dash p squared f. If I multiply everything by r squared, or possibly not. Anyway, it's one of Bessel's equations, which months ago they mentioned. Yep. Oh, well, here's one I prepared earlier. Bessel's equation is an equation of this format. It has an x squared or an r squared, if you will, y double dash, and an x y dashed, and a minus x to the 4 by the look of it. I could be wrong. Oh, no, that squared's not there. It's here. Yep. Wait, just a second. This is Bessel's equation. There's also Bessel functions, which are a different thing. So Bessel's equation is a differential equation. It looks like this. And let us compare to what the notes say. The notes say f double dash plus 1 over r f dash plus p squared f. If I multiply that by r squared, I'll get r squared f double dash plus rf plus r squared p squared, which is one of these. Yep.
So they incorporate like Bessel functions into this this drum as well, like with obviously Bessel equations.
Yeah.
Is there, could you like attempt to explain it a bit better? Is the note kind of like
Well, so that I don't know. I'm doing my best here. As far as I can tell, if you do the circular drum thing, it happens to produce a differential equation which happens to be this shape. And when Bessel was studying differential equations, whenever Bessel studied differential equations, Bessel discovered that the solutions to these equations are Bessel's functions, which are weird and are shaped like this. And Bessel's functions are some weird-ass infinite sum. Taylor series. I believe. Could be wrong. Possibly both. Okay, so when I was reading the notes this morning, when the revision seminar that I thought I had on, but when I emailed the students, I forgot to put their email addresses in, so nobody turned up. When I was preparing for this seminar this morning, I was reading through it and it mentioned Bessel's equation, and there was a little note at the bottom of the page that said, sometimes when you solve PDEs, knowing what the solution to Bessel's equation will be useful, which is a little bit like the wizard saying, here is the sword of entitlement. You'll know how to use it at the proper time. Okay. Okay. It's a plot coupon. And it's still not. It's just the fact that it's a Bessel function might be, I don't know.
Like, I swear we did, like, I remember doing it, but I think it wasn't exam.
Yeah. Have we got that in writing?
Yeah.
Okay, but this is where we are. So it turns out that this number nu here, we'll call it v because it looks like a v, but it is technically the letter nu, a small nu. If it's not an integer, then we get two Bessel functions of the first kind, which are called j, because I don't know. And if v is an integer, we have a Bessel function of the first kind and a Bessel function of the second kind, which is called y.
So how do we actually use that? What does that actually mean?
We find a machine which knows what the Bessel functions are, such as MATLAB.
Wait, we don't have to use that.
Correct. So if you were in the exam and someone asked you, what's the solution? You would say this.
And that's it.
Yep. Sorry? Yeah, okay, cool. I'm going to look that up. Thanks, Jordan. Okay, so just wait. I don't think that's supposed to be a P. Anyway. Oh, yes. Oh, okay. No, it is. Okay. That's all right. Oh, S is P times R. Of course it is. Right. So what happens is, because this is a Bessel equation whose nu is 0, it produces these solutions. So we get two different solutions, a Bessel's function of the first kind and a Bessel's function of the second kind. And these solutions must be a linear combination of those, because that's how it always works. It's A of something plus B of something. And it turns out that because Bessel functions of the second kind have the property that they go to minus infinity as s goes to 0, we can't have any of this, because the displacement is not minus infinity, because it's an actual physical drum. It can't be displaced infinitely far from the position that the drum is, because it's a drum. It's not an angel's drum. Oh, there's a function called Gabriel's horn, which is an infinite function. Okay, and so therefore we end up with, magically, the solution is a Bessel function of the first kind. And when we sub in the condition, it produces the fact that Bessel's function has to be 0 at the places I'm thinking of. So what is the moral of this tale? Sorry? No. Nope. First time. They didn't do this last year. I don't know. I don't know. But the moral of this tale is that if you start with a circular drum, which has initial conditions that are reasonable, where the initial velocity is 0. What the hell? Where's the t? Oh, okay, cool. There's no thetas anymore because we assumed all of the directions were the same. So we don't need the theta. So it's just r and t. Okay. That's important. So if you start with a circle drum and you assume that all of the thetas are the same, we don't need the thetas it's the same in every direction. We don't need the thetas anymore. We only need the radius then. So they're gone now. They're gone now. And we assume that the initial velocity is 0 because that's to do with hitting the drum. And then we do all the things. We will eventually get to the solution that this, which I don't think you need to look up or even remember. But the very, very important thing is this. P which is the P which is where the hell is the P? Yep. What is S? Okay. Oh, P is what percentage you are from the center to the edge. Yeah.
It would be really great if they told us this information.
I could be wrong. No, I'm making that up. No, just a second. No, it is. Yeah, when the radius is 0. No, I have no idea, I'm sorry. Yeah, and so the P is going to end up being, yeah, okay. It came from there, right? So this would normally be a WN in that spot if it was WNX. Yeah, no, that makes sense. I like it. Comparing to the other one, in the old one we had WNX, like omega NX, and now we have P times R because our variable is called R. And we just relabeled that S for reasons. Okay. So, normal modes. Where's the nodes? Sorry, I'm just getting really angry. Yeah, but there was a thing about like a nodal line. So a node is a place where the displacement is 0. Is that right? Where was it? This graph here? Okay. All right. All right. So we have now got node equals place where the displacement is 0. And because this is a circle and it's vibrating up and down, and it's the same in every direction, if it's going up here and going down in the middle, there'll be a circle in the middle where it's not moving. Is that the idea? And so those will be nodes. They will be lines made of nodes. So they will be nodal lines.
So like to visualize this, correctly, of if you just drop a stone in a pool of water.
Yep. And so it'll be going up and down. It'll be going up and down here, but this one will be going up and that will be going down, and there'll be a bit in the middle that's not moving at all. Okay. Sorry? That's a great question.
So what's a PDE?
Wait, hang on, slow down. Hang on, it says K equals alpha n on R.
And the solutions are this. Oh, okay, just wait. We've got a cos and a sine, which is causing the wiggly bits. And then we've got the times by the Bessel function. So what's the... So wait. The nodes happen when this is 0. Right, that's the nodes. And the nodes happen when the P is equal to a root of the Bessel function divided by the radius. That's what that says.
And then alpha n is just calculus, we have to do it up.
Yeah.
So the alpha n, yeah, we have to either know off by half or half.
Yep, and I don't expect you to know it by heart. So I think the nodes happen when the P, whatever P is alpha n on R, where the alpha n is the nth root of the J naught Bessel function. I don't suspect we're going to need to know this, but this is what's going on. The words we've used, I at least definitely know how to interpret why this is equal to 0 because it's the edge of the drum. So I'm doing okay there. And show it to next year's students near the beginning and they can see people muddling it through and going, I have slightly better than not. Okay. We are doing okay. And I don't think the rest of them have all that much more stuff. I've got heat occurring on page 110. Which is this, in one dimension. Yep.
So because we don't really know Bessel functions like that well, that means we can't, like we still have to get used to the separate function, not have it.
Yeah, basically they've introduced it to make you believe that you can use differential equations to solve things for drums. Or possibly make you believe that differential equations are useful for something. I think the ultimate result was just confusing everybody and making them wish they'd never seen it. I think so. I don't know. We're tired. Oh, I mean, acoustics, obviously. No. But differential equations apply to any situation where it's easier to describe the velocities and the accelerations than it is to describe anything else. And it's all physics. So fluid dynamics, how fluids flow through things, is all differential equations as well. So just a second. So with the string, it turned out that we could actually do that ourselves. That's one we could do ourselves. We could do the separation of the variables, we could find the Fourier series, and then we'd have an answer. And we can figure out from that one, based on the information we've got fixed at both ends. We know what initial displacement means. It means the shape of the string. We know what initial velocity means. It means the speed of the string at every particular position. And we know what to do if that is 0, basically. And then the drums come in 2 flavors, and there's a lot of stuff going on, but it turns out that what we're interested in is the frequencies and the positions of the nodes, apparently. Okay, so, and this one, the frequencies, there was a formula for that based on the size of the drum. And with the nodes, that was when the function was equal to 0, and that will happen when you're like 2 pi whatever times the frequency, because they're causes and sines, okay? And this one, they didn't talk about the frequencies, they only talked about the nodes, and that happened at the zeros of the Bessel function because of the differential equation producing that. So I guess the idea is that saying that, look, there's a lot of moving parts, but it's possible to get an answer from for the thing that you want, even if you don't have a very nice answer for the actual final answer. Okay. So the heat equation was similar to the string equation, except it was only one derivative here instead of 2. And the phi here stands for the temperature, I'd say. Flux. Now, where's the flux? The flux is the Q. Concentration molecules is phi. The flux is Q, so that's how quickly the molecules are moving. Oh, okay. So we're thinking of like a... Okay. So it might be a gas, right? And there'd be particles flowing around everywhere. And so they'd be moving at certain speeds, and there'd be a certain density at certain places. They'd be thicker in some places than others. Okay. And both of those variables... Oh, interesting. So you combine those two together and you end up with this. And the phi is the concentration of the molecules. Okay? The heat equation is a special case where we get this. What does delta squared mean again? Oh, this is in 3D, okay. Yeah, that represents, yeah, the gradient of, yes, it's the curl of the gradient, something like that. Like it's a multivariable calculus thing. Okay. But in one dimension, you don't have to worry about that thingy, it just becomes this. Okay, so that was all just telling you that the physics is real. Okay. And now we produce this equation, which is exactly like our string wave equation, except that on the left-hand side, it's only one derivative instead of 2. Okay, that's the difference. And then it's saying it's insulated. Ah, here we go. Here's the words. It's insulated. Insulated means that it stops the temperature changing. So, yep. And so that's why they're saying that the temperature at the left-hand end of the bar is 0. Because we don't care what the temperature is, we just care what it's different. Like this would be declaring that whatever temperature you want it to be is 0. Much like Celsius declared that the freezing point of water is 0. But it could be 500 if you wanted, like if you were heating it at that end. So I think that insulated is what's causing this to be 0 here. Because it's, yeah, I don't know, I could be wrong. Maybe it's insulated, or no, it's insulated around the bar so that the heat doesn't go out the edge. Oh, all right. Only a single initial condition is required. That's okay, because there's only 3 derivatives, so we only need 3 conditions. I'm good with that. So the initial condition would tell you what the temperature is at every location at the time equals 0. And it would usually be a function. I'm just thinking about this. So are we assuming that the bar is a particular temperature to begin with, and it's insulated everywhere, and so we're just going to let it sort itself out, and the heat will travel one way or the other, right? So you could be filling it with hot water and going, or heating it up at certain spots and going, this is what the temperature is right now, and I'm just going to leave it and see what happens to it. I think that's the idea. And so you would have as well, just want to write this down. So it's not actually technically heated, it's just heated to start with and then you stop heating it. I think that's the idea. So you heat it to start with and it's this long and then it's various temperatures. You know, this might be cooler and this might be hotter here and it's really hot here and it's really, really hot here and not so hot here and cool, something like that. And that's the initial temperature with where the vigorousness of my texture colouring in is the heat. And then we wait to see how the heat spreads out. So you would expect it to sort of all spread out to be even by the end. That's sort of what you'd expect it to do, I suppose. If it's insulated everywhere. And so we're assuming that the edge temperatures are whatever I declare 0 to be. Yeah, because that's the insulation that they're talking about. The temperature at the left-hand end for all time and the temperature at the right-hand end for all time, because I've got something there that's stopping the heat from getting in or out. Okay. And then I've got the temperature at time 0 will usually be a function of x. And this is my function at the moment. So I heated it to a certain way and then I left it. I think that's the idea of what's going on here. And then I do the separation of variables, but it behaves differently this time. The F double dash still produces the same thing with the sines and the causes, but because of the heating at the opposite ends, we end up with just a sign. And because the other one is a single variable solution, single differential equation, we get an e to the power of. And so we get this thing. And there would be infinitely many of them all added together. And it's already behaving the way I think, because e to the minus thing should go to 0 as t goes to infinity. So the temperature should all even out by the end. Determine the heat conduction in a thin bar for the initial profile that. New terminology. Initial profile is apparently the initial temperature. And heat conduction sounds to me like I'm going to decide that what they want is the formula for what the temperature is at a particular spot at a particular time. Because heat conduction is about how the heat moves. And so that's what heat conduction would be. Right. The capital T as a formula. Yep.
On the last page, so step 3, we don't have. What is step? Oh, step 3 is disposition.
Step 3 is the infinite sum of those things, and then you get told what the initial profile is, and you figure out what the coefficients have to be in order to make that work. Yep. Okay. There was one more. I wish I had a summary of this, and maybe one day I'll watch it and I'll write down all the notations. No, where is it? There was an electromagnetism thing, which is this one, which I don't think they even did. There's no answer for this, so I think they just didn't even care. Yeah, did in a lecture. You say just like it's...
But like, it's not a whole new thing that we haven't gone through. It's like
It's a whole new thing that I've never seen. Yeah, so this is a new equation with 3 variables. And in this story here, it's a rod with uniform circular cross-section being charged from the top and under static conditions, those words mean things, apparently. So this is saying that the charge, that's what the phi is, the charge?
Yeah, so the blue charge section is orange is not charged, and
Oh, so we're looking at it like, oh, so, no, it's all right. But this rod, the top, that's the blue bit is the top of the rod. Yeah, it's like this. That blue bit is this bit, and the red bit is this bit. Okay, good-o. And then, so there's a charge on the top, there's no charge on the bottom, and so there'd be formulas that tell you what the things are. Okay, I choose not to look at that right now. I don't think this is going to be a thing in the exam. There's too many variables involved all at once. Do you think did they switch to polar in one direction? All right, so you're not going to be expected to do that yourself. So I'm just skip it. That's my instinct. So they are, I don't know, it's time for someone to say what have you learned, what they've learned, or how they feel, or both.
Feel better about, I think, John's group and less better about the differential.
Yeah.
Yeah, if it's a string, I'm going to do it. If it's not a string, I'm not.
Yeah. Okay.
Exactly, skip the questions, right?
Yeah.
Okay.
Exams are all about preparation. Prepare the questions and get them once. That's questions.
If things were different than they are, I would do a seminar tomorrow. Give me a second. Yeah. It's just at the Maths 1A exams on Saturday. It would be really nice to have something that had the Fourier transforms. Sorry? So,
Is there any pre-recorded comment?
of course there isn't. They didn't do it last year, and that was the first year that was in there. So that's the problem. Like you are now experiencing what it was like back in 2011 when I did the first revision seminars, and there weren't old ones to look at.
So for this course, have I just added in a bunch of extra stuff on top of the old stuff? So there's more than one.
Well, they cut and pasted things from several courses. They did a bit of these courses cut apart and put together to make new courses. But the Fourier transforms weren't in any of the courses before, and they've put them in now. Yeah, because they thought they had time. So just a second, I'm just going to stop the recording there. Those who are listening, there may be another video to look for. Good luck. I'm going to stop the recording.